So today we're going to discuss a bit on the ANOVA. This is a very big topic. After this lecture, you should understand the concept of ANOVA, why you have to use the ANOVA. And you also understand the differences between one-way ANOVA, two-way ANOVA, and also the interaction effects between factors. After that, then you should be able to perform statistical tests for one-way and two-way ANOVA. Okay. First, we'll discuss briefly about analysis of variance, why we need to use analysis of variance, what is the characteristic of the analysis of variance. So after you have some basic understanding on this, we'll move to the one-way ANOVA. So this is to deal with only one factor at a time. Okay. Then after that, we move to the two-way ANOVA. Then this one is deal with the two factor at a time. Analysis of variance. So far what you have learned, okay, you learn how to use the Z-test and T-test for your research question related to the differences. Okay. So far what you have learned is just the differences between two samples or two groups. So today we're going to learn ANOVA, which allow you to test the differences more than two groups. So this is a purpose for ANOVA, to test more than two groups or treatment for each factor. So the factor can be one factor, can be two factor, can be more than two factor. Okay. If you have one factor, we call it one-way ANOVA. If you have two factor, we call it two-way ANOVA. If you have three factor, we call it three-way ANOVA. Okay. So for example, factor. So factor can be a gender. Okay. You want to test is there any differences between male and female. In this case, you only have two groups, but you still can use the ANOVA. In this case, you only have one factor. In this factor, you have two labels. So what we call the label in the ANOVA. So one is a male, another one is female. Okay. So example of the two-way ANOVA is that in addition to the gender, maybe you have another factor. Which class the student belong to. So maybe there are three classes. So this is another factor. Then in this factor, you might have three labels. So class A, B, and C. Okay. So in normal cases, if you collect your data, okay, so you want to test is there any significance between the body height, okay, between the gender, and also between the different classes. So in this case, you take two pair of the hypotheses, two different set of hypotheses. So you have one alternative hypothesis to test is there any differences between gender, okay. There is no differences in body height between gender or male and female. Okay. Then the alternative will be there is a differences. So this is one pair of the hypothesis for one factor. So if you have two factors, then you have another pair of hypotheses. So in this case, maybe you want to test is there any differences? No differences between in the body height from the student of different classes. Okay. Then the other one is there is differences. Okay. So in this case, when you collect your data and you organize your data, then your data should be in this form. You have two factors. One is gender, another one is class. So this is first factor, this is second factor. Okay. Then you also have a response variable. So in this case, it's the body height. So each row represents each of the student explained unit. Okay. So this is how you collect the data. So the analysis of variance can be one way, in which it involves only one factor, or it can be two way, two factor, three ways, and so on and so forth. And for each factor, there can be more than two labels, 3 labels, 4 labels. This is one of the example. So for example, this is the first one. So there is no effect of the treatments on the response variable of exponent unit. So now we're talking about one factor first. Okay, start from the basic, one factor, one-way ANOVA. Okay, so this is type of the question related to one-way ANOVA. So in this case, you have more than two groups. Okay, so you might think that why not we just use a t-test, because you can compare, because the hypothesis is there's no differences or effect of the treatments, right? So there's no differences in the effect of treatments. You might think that you can do the t-test, just run 3 separate t-tests. Okay, the first treatment with the second treatment, you run 1 t-test. The second and the third run 1 t-test, and the first and the third run 1 t-test. Okay, you can do that, but it's not appropriate to do it like this. Okay, there are a few reasons. Okay. So for example, if you just run a pair of the comparison between the first sample and the second sample, first treatment and second treatment. Okay, so this is your hypothesis. And for each statistical hypothesis, you always have a alpha, the significant level that you set. Okay. And also, the alpha means the type 1 error, right? So that means that you might reject the null hypothesis even though there's no significant difference. Okay, so that means that the probability you correctly not to reject the null hypothesis is 1 minus 0.05, and this is 95%. Okay, so this is for one test. So if you run multiple tests of two comparison between two samples, the t-test for example, then you have the alpha level for each of the tests. Okay, so that means that the probability correctly not to reject the null hypothesis for 3 separate tests is this one. It's no longer 0.95, but it's this one. Okay, so it's 0.86. Okay. So that means that the probability that you incorrectly reject the null hypothesis, which is a type 1 error, is 0.14. So it's no longer 0.05. Okay. So if you read some statistical textbook, they will say that there's a way to correct this one, right? Okay, you still can perform multiple sample tests, but preferably if you can use only one single test, we prefer to use one single test, which for the particular test, the alpha level is 0.05, rather than run 3 separate tests and then need to recalculate the alpha value. Okay. So in the one-way ANOVA, the hypothesis is slightly different from what you have seen in other tests. For example, for t-test, in the hypothesis, you will see the parameter, right? Okay, you will see the mean 1 equal to something like this. Okay, and for the so this is for t-test. For alternative, it's something like this. Okay. However, in ANOVA, we do not write the hypothesis in this way. Okay, we write in sentence. For the null hypothesis, it's okay. Okay, the mean 1 is equal to mean 2 equal to mean 3. You can write in this way. Okay, but for alternative, okay, it's very hard for you to write all the combination, because the alternative is there is an effect, so there is a difference. So the difference can be all the 3 are different from each other, or maybe only the first one is different from the other 2. Or only the later 2, the sample number 2 and number 3 are different. Okay, so that's the reason why in the ANOVA, usually you write in the sentence. Okay, okay. So what you can write is there is no effect of treatment on the mean of mean response variable of the exponent units. Okay, we do not write in this way. Okay, if you write the null hypothesis in this way, the alternative you have to write in this way as well. So, but there's a lot of the different combination, right? This is just 3 samples. You can imagine if you have 4 different samples or 4 levels for each factor, then this will be very troublesome. Okay. So for ANOVA, if you write this way, everyone should understand. Okay.